Hi everyone. In this video we're going to talk about lesson 8 of the particles and energy scheme of work, which is about temperature and energy. And it's an opportunity to understand, to introduce, I beg your pardon, a really important distinction between temperature and the kind of intuitive understanding we have of that, which is hotness. So ask most Year 7 students, what do we mean by temperature? They'll tell you it's how hot something is. Now, for everyday life, that is a perfectly good definition, because that's what temperature is. If it's a high temperature outside, it's a hot day. If it's a low temperature outside, it's a cold day. But if we want to be more precise about hotness, so to speak, it's actually quite difficult because human beings are very poor judges of temperature. So you might have seen the classic example where you take a metal object and a plastic object, or any conductor, any insulator, and you hold the two together and you say, well, which is at the higher temperature? And you would always say the insulator, because thermal energy is not being conducted away from your skin as fast in the insulator as it is in the conductor. But of course, these two are both at room temperature. They're both at the same temperature. We're just very bad at judging that. And this is why we need a better definition of temperature than hotness. Hotness is a kind of qualitative description. It's hot or cold. It's a way of describing it. What we want is a quantitative value. Now, I'm getting a bit ahead of myself. I don't think I'd go into kind of that discussion right now with Year 7. That I saved that till Year 9, that difference between qualitative and quantitative. But what we're going to do in this lesson is introduce that idea that actually temperature is something that's measurable, and it's all to do with the kinetic energy of the particles. So the way I introduce this concept of temperature, and that's what this whole lesson is about, is basically about getting them to understand that temperature is just the average kinetic energy of the particles in a substance. The way I introduce that is to tell a little story about a block of ice. And I asked them to imagine that you've got this block of ice, and I would draw this in here. So let's draw a block of ice like this. Just a really simple cube, something like that. You could even just do a square, that would be fine. And I'm going to say that's just been taken out of a very cold freezer that's at minus 20 degrees C. Now, I always start with a kind of concrete picture, so in this case the block of ice, and then I zoom in into our more abstract model. And again, this builds on this idea that we keep talking about all the way through our science curriculum, which is science is understanding things that you can see in terms of things that you can't see. So we can see the block of ice, what we can't see is the particles. But if we think in terms of the particles, we can understand what happens with the block of ice. So this is a nice chance to recap. What does it look like in here? Well, our simple particle model says they're very close. The particles are very close together. They are in this fixed lattice, this regular arrangement. Fixed means they don't move. All they can do is vibrate. And what I might show here is that, okay, they are vibrating, but just a little bit. So I'm just going to draw one line here like this. So I'm going to bring in this idea that they are vibrating a little bit, but not that much. So they're just moving on the spot. But what I'm going to say to students is, okay, what we're going to do is warm up this block of ice. Now, when I tend to do heating, I draw diagrams for heating, for some reason I tend to use a candle, just because I guess it's easy to draw. So imagine I'm holding a candle somewhere near this block of ice. Just some way of illustrating that you're passing some heat energy to this object. Now, this is where you could do a separate diagram if you wanted. That might take a little bit long. So what I sometimes do is say, okay, if I heat up this block of ice, well, the temperature of this is going to increase. So let's say it's no longer, after I've heated it, it's no longer at minus 20, it's gone to minus 2 degrees C. Okay, I still want it to be solid. I still want it to be a block of ice. And what I would show to students is the difference between minus 20 and minus 2, that increase in temperature. And again, this is a bit challenging maybe for Year 7s because we've got negative numbers, but as long as they recognize that when you put heat in, what happens to the particles. What I want to show to them is that as you increase the temperature there, what you're doing is increasing the kinetic energy of the particles, i.e. they're jiggling more. I'm going to show this, that they're going to keep jiggling a bit more and a bit more like that as I heat up the block of ice. So you know, the reason I've done it like this and done the kind of crossing out bit is just so I don't have to draw the diagram again. So it's just maybe save a bit of time. So what I want to do is show that as I heat it, these just jiggle more and more and more and more. But we get to a certain temperature where instead of just jiggling more and more and more, actually these particles start to break free of these strong bonds that keep them within the lattice. And I would tell them that the temperature at which this happens is 0 degrees C. So at a certain temperature, which in this case we're going to call 0 degrees C, something interesting happens. So when I draw my diagram like this, in fact, firstly, I should start with the concrete. So what I'm going to do is show this kind of block of ice now beginning to melt. So I might show it like that, and then I might show a kind of little puddle forming around it, and maybe even some little water drops coming off like that. So what I've got is this change of state, which we call melting. So I might put melting here like this. And again, this is nothing students won't be familiar with. But what I want to do here is show them, okay, this is something we're all familiar with. We've seen snow or ice melting. But what's happening in terms of the particles? Well, if I were to zoom in on what's going on here during melting, this is what would happen. This is what I would be able to see. So I would still have some of the particles left in my lattice, but I'm not going to draw all of those particles. So I want to show that actually quite a few of them have now broken free. And these are jiggling quite a lot, like the ones we saw in the previous diagram. These still have the same amount of kinetic energy, or even a bit more than we had at -2. So these have lots of kinetic energy. They're jiggling all over the place. But what I want to explain to students is that what's happening is some of these are jiggling so much that they're managing to break free. And they've got a little bit of kinetic energy with which they can move. But these particles are not just moving all over the place. They're still quite close together. But they're breaking free of the lattice, okay? And I might want to allude to something that we'll come to later on, which is during this change of state, the particles themselves are not changing. All that's happening is the bonds are being broken. So I might put something here about bonds break, something like that. And the other thing that I think is worth referring to here is when we have something like this where the particles themselves don't change, we just have changes in energy and arrangement and motion and so on, then what we would call this is a physical change. So I might add here physical change. Now that's something I'm not going to dwell on too much until I get to the second unit, which is on an introduction to chemistry, where they see that distinction. But I do want to tell them that this physical change, all that's happening is the arrangement of the particles and the bonds between the particles and their energy, in effect, is changing. And it's something that can be reversed. So it's something that I might introduce while I'm talking about this. But it's not the most important part of this lesson. The most important part is them getting this idea of temperature. Now then, what I might do is show, well, okay, if I were to heat this block of ice a bit more, and again I'm going to use my candle to show heating, well, what I would end up with is some water. I'm going to draw a kind of pool of water like this. I mean, actually what you'd get is some evaporation, but we're not going to worry too much about that now. Maybe it would be better actually to put this in a glass or a vessel or something like that. But anyway, let's bring it up to about room temperature. Let's say about 22 degrees C. And it's a good opportunity to introduce room temperature if you didn't already do that in the previous lesson. So if I were to zoom in on here, well, what I want to show here is if I've continued to heat my water, then all that's going to happen is I'm going to have my particles. Now they're all in the liquid phase, so they're all close together but not in the fixed lattice. They're randomly arranged. I don't know how many particles I've got there, but it doesn't matter too much. Let me move that down. And what I want to show is that where here I had quite small arrows because it was only at
0 degrees C. Here, because I've now gone up to 22 degrees C, I'm going to have longer arrows because the particle is going to have more kinetic energy. And remember, what I want to do here is get across this idea to students that as this number, this temperature changes, really that's just a measure of how much energy the particles in a substance have on average. And again, you can stress on average because not all the particles are going to have the same speed. They're going to have arrows of different lengths. In fact, maybe I should exaggerate this a bit more and make these a bit longer. But what I want them to see is that on average they have longer arrows than in the diagram above, where the liquid was only at 0 degrees C. Now you could carry on this story, and you can imagine heating this water a bit more. You could show the change of state from liquid to gas, where some of these have so much energy that they break free and start to rise up elsewhere, and you know, we'll go into evaporation in more detail in a later lesson. But for now, I'm just going to leave it here. Just a reminder, the really important point of this lesson is about what is that definition of temperature. Because if they can make that really clear link between the average kinetic energy of the particles and the temperature, this number that we give to hot or cold substances, that's going to give them that much deeper understanding of temperature than if they're just talking about it qualitatively in terms of how it feels, whether it's hot or cold. So however many diagrams you do, I think it's really, really important. That is what you want to get across to the students. Okay, I'll leave it there. In the next lesson, we're going to look in more detail at what's happening here at 0 degrees C when we look at melting and boiling points.